Hello everyone, my name is Faranak and I will be presenting our study for tissue classification using iKnife data. During a cancer surgery, the goal is to take out all cancerous cells along with a margin of supposedly normal tissue. Success of the surgery is validated by histopathology examination of these margins, so real-time assessment of margins during operation will be beneficial. iKnife is a new modality that can extract the chemical profile of the tissue by analyzing the cautery smoke intraoperatively through mass spectrometry. Mass spectra can be analyzed further to differentiate between cancer and normal tissue. Graph convolutional networks, or GCNs, were originally designed to incorporate the structural information of graph data into analysis. In some applications, like the analysis of brain connectivity, the graph conversion is straightforward. But in medical image analysis, for instance, the relational structure should be further assumed. Our objective in this study was to propose methods to convert iKnife mass spectra to graphs and use a GCN network for basal cell carcinoma or BCC margin detection. In our workflow, point burns were recorded from BCC patients along with pathology labels. Mass spectral data were defined by the ion count plotted along each ion's mass-to-charge ratio, or M/Z. The analysis includes pre-processing and converting the data into graphs, building a graph network with GCN layers, a readout function, and fully connected layers for graph classification, and finally evaluating the trained model. In our first proposed method for graph conversion, we assumed a structure in which 50 M/Z subbands were considered as nodes and only connected to their immediate neighbors. This approach resulted in graphs with 16 nodes and 15 edges. In our second approach, we considered 50% overlap between subbands and a multi-resolution level architecture. Edges were created between immediate neighbors as well as between subsets in immediate resolution levels. We continued this until the entire range was represented by one node and 50 features, and the spectrum was converted to a graph with 57 nodes. We achieved best results for our multi-layer representations. This outperforms the PCA-LDA, but is comparable to the autoencoder-based classifier results of a previous study without performing any data augmentation. So, according to results, incorporating structural information into learning framework has compensated the lack of a large dataset. To conclude, these results confirm the efficacy of using our proposed graph conversion approaches along with the GCN network for margin assessment. Thanks for listening.